So a couple of weeks ago, Jeffrey Bloom, who's actually been running this session here and who's the Director of Graduate Education for the Data Science Institute, had a neat idea. Why not demonstrate machine learning by preparing some data before the symposium and then start training a model at the beginning of the symposium, and then at the end of the symposium sort of show the results of having run this analysis. So I made an additional suggestion and managed to grow Jeffrey's original idea, his neat idea, into a fully developed, bad and risky idea. And I said, hey, let's do deep learning, and hey, let's do it on a data set that we collect during the symposium, and then we'll show the results. And I've been regretting this suggestion ever since. So why would I even consider this? Why would I even think that this was possible? Well, in actuality, deep learning frameworks have come a long way. And modern frameworks have done away with much of the boilerplate code which usually would consume hours of your time. There are helper functions that handle much of the repetitive work and that also make good initial choices for you. In addition, pre-trained networks have really vastly reduced the amount of time and the number of training samples needed to create a well-performing deep neural network solution. It's changed the world. So let's go and take a look at this just a little bit. This is some sample code in a framework that I used for this work called fast.ai. And the purpose behind this is to develop a detector for different types of bears that you might find in the wild or the bedroom, because there's teddy bears, and there's grizzly bears, and there's black bears. And it turns out that this is about all the code that you need because so much is happening in the background here and handling it for you. Pre-trained networks. So this is a ResNet, a residual network. It's a couple of different things. One, it's a slightly different architecture than most other networks, and it also has been pre-trained. So it's been pre-trained on ImageNet information. So it's already been exposed to a great deal of information and images, and has essentially formed the analog of a V1 visual cortex within the lower layers of the network. So that means you can get by with using less information to train the networks. And here's the trick. Here's kind of what it does. So here what you do is you take this pre-trained network with all of its convolutional layers, then you add on some layers at the very end. And the layers that you add on the end are the ones which are supposed to come up with the final answer. Was it teddy, grizzly, or brown bear? And you can do two things. One, you can train this just the last few layers, leaving everything else frozen. Or you can actually train some of the later convolutional layers as well, which will do an even better job, so long as you have enough data. So, and the idea here is you unfreeze, and then you begin to retrain. And there's been some real advancements even just in the last 6 months. When I last looked at the fast.ai framework, the real success in the examples that they were using was the cat versus dog detector. So based on images from Google, you could train a deep neural network that could differentiate between dog and cat really, really well. And that was really impressive. Well, I go back and I look at this and what they were doing for the last version of this, and now they're doing over 24 breeds of cats and dogs, and it has incredible accuracy. And so the changes that have occurred even recently have been really profound. And it's not that the network architecture is changing, it's really almost tweaks. It's almost things like a new type of an approach for learning rate and for changing that slowly or quickly over time. But these make profound differences in how quickly these things can be trained. So it occurred to me, even with all this great tech, I had really better have a backup. As Andreas has been commenting sort of throughout the day, we don't know if it's going to work. So I had a backup. And so I was thinking, if we can classify, Pekingese and poodles from images, why can't we classify professors? Why can't we classify psychologists and statisticians in the same way? So I trained as a backup a professor predictor. So, taking a look, all right, going to Google Images and scraping images of mathematics professors or of English professors. So 10 different breeds of professors to see if it's possible to classify these. So something interesting here. When I went about and started to work on training up this network, I used exactly the same type of network that was that's shown here, a ResNet, used ResNet 34, and then prepared everything. And here's my code. My code is on your right. The original sample code is on the left. There's not a whole lot of difference here. Matter of fact, it's really just one line, me telling it what the categories are going to be. And other than that, the code is exactly the same. So where is the code? Well, the code is in the data. As a matter of fact, what this points out is that the code is buried in the weights within the network. So it's buried deeply within. And any programming that I was doing was simply in the selection and the curation of the images. So you may have heard the phrase, your data is your source code. This is exactly what it means. There is no code here except for the images that you choose to train on and what you choose to do with them. So that means that if you want to be able to speak to how the network was trained, versioning your code won't cut it. You can version this code all day long, and it's not going to tell you anything about the network. You need to also be versioning your data, which is a challenge that most of industry and some of academia is not quite up to yet. This also means that we have some real-world problems here, that bias in training data will be memorialized in your model, hidden almost as certainly as if you encrypted the software and injected it in. Any bias which is in your data is going to end up in your model and in a way that's not directly interpretable. And that's one of the risks of using deep learning. All right, so this is how I trained it, but now let's see how it did. Yeesh. All right, so what does this mean here? This is a confusion matrix. So this means if you are in archaeology, congratulations, you're recognizable as an archaeologist. If you are in art history, you need to up your game because you're not identifiable. People tend to confuse you with chemistry professors and sometimes with engineering. And then there's some really interesting oddities here, like, check out psychology. Psychologists get confused with chemistry? All right, so it's easy to look at this and say, terrible, terrible network, but let me actually give you a quiz. So train the network, and I chose the top misclassified images and the ones that were most harmful to the overall performance. So you can actually classify and you can see how certain the network was about it and whether it was wrong. And this contributes to the overall loss. So these are some of the top loss makers. So here are the areas. Art history? What's the best guess? You can just shout it out. What's that? Pharmacy? Except pharmacy, closest you're going to get is chemistry. I had to draw the line someplace, so I couldn't have every discipline. So you think chemistry? All right. You think? Model predicted chemistry too. All right, yeah, very good. Oh, except it was wrong, right? Because these are the ones that cause your most loss. This is engineering. Okay, now this one's not fair because it could possibly be chemical engineering, right? But the fact is, we got it wrong, the model got it wrong. Okay, here's another one. Best guess. Math? Okay. I know, English. It's like if there's nothing there, right? Like, oh, it's English. Hey, that's what the model thought too. It's chemistry. All right, here's another one. The model gets to use anything it wants to. It's not just using faces, it's using things in the background, right? Math? Okay. So we think math? It says math. But you think statistics because it's not math necessarily? Whoa, very good. Did you recognize what was happening in the background? It kind of looks like, yeah, exactly. Yes, that's exactly. So if you look closely and if you know enough, then you can differentiate. But first, you think math. It's a chalkboard. All right. Chemistry? Model said chemistry as well. It's engineering. So engineering is one of those things where they get to play with lots of really cool equipment. That was one of the things that I was kind of resentful, as I was doing, my PhD in quantitative psychology. It was like, I got no cool equipment. The engineers got it. The other folks had it. All right, one final one. No guesses? Art history? Kind of a well put together person. You think maybe it's exactly what the model thought as well, was art history. Computer science. All right. So, yes, the model wasn't doing all that great, but we are not doing all that great either. It's probably doing as best as you can, given the kind of information that you have there. So, So this got me to thinking a little bit, though, looking at these pictures and the fact that you're getting information from the background. And I was thinking, if the pictures weren't posed, because remember, these were all on the web. These are like, hey, I'm going to take a picture of someone, and I want people to know that this person is a mathematician or computer scientist. But if we took pictures that were not posed where you were, but were just in a common area, taken in a consistent, controlled manner, say, as people were checking in for a symposium, would it be possible to train a network on the images? Now, pre-trained networks do really well, but there is a minimum amount of information which is needed, so it was not going to be possible to try to do departments. However, what about a professor versus graduate student versus postdoc versus industry? Now, that's something we might be able to do. As a matter of fact, this is generalizable and could produce a useful product. So, grad students, put yourself in this space. You're actually taking a break in the lab. You're putting the high-def, large-screen monitor to good use, catching up on Games of Thrones. Wouldn't it be helpful to have a professor detector set up in the hallway? And so if a person walked up who was likely to be a professor, it would, automatically switch you over to the lab results you were going to be looking at. Faculty, this is for you as well. Let's say that you have a large conference with very attractive snacks placed in a common area. Wouldn't a graduate student detector be handy just to safeguard it until the attendees could actually leave for the snack time and then, yeah. So, useful product. So, how well did we do? Because we needed data to be able to do this. Yikes. Graduate students, we had we had like 100 that were registered. We only got images of 55. Professors, we had 89 registered. We only got 43. So I think of this as a plane not really well designed, trying to take off. It's right on the edge. I was kind of sweating bullets because the validation set for this, which is going to be 20%, is going to be like 17 images. So this is about the lowest that you could go. So, I actually had someone who joined me out there, a partner in crime, as we were sort of looking at different possibilities, Richard Galvez. So thank you very much, Richard. It was a lot of fun sitting, and Richard got to see a fast.ai for the very first time as well. So let's go ahead and go to the to the notebook, and let's see how we did. So again, here's the notebook. Again, very simple code. This is actually doing everything for us in terms of pulling in the data and also doing any transforms on the data to introduce jitter, a little bit of rotation, some flipping in order to augment the data. We actually tried it two different ways, one with and one without. It also reduced the size of it slightly and just talked about normalizing the data. This is the data as it looked like it when it was brought in. There you are, Andreas. And the labeling. So that's why it was so fast. That's why I said, hey, let me take your image. Are you professor or grad student? I just dragged it to the right subdirectory, and there we were. So this is the one line which defines what the network's going to look like. ResNet 34, and that we are going to be adding additional layers onto this and training that up. So here's what we landed on. This is a fit one cycle. This is one of those approaches, one of the tweaks I was mentioning to you before, that manages changing the learning rate in a way that turns out to work really quite well for most instances. The one thing we were not able to do, though, because we simply did not have enough data, was to do this unfreezing and retraining of this convolutional part. We were only able to do the last little bit there. So performance, we didn't have enough data to get it to be much better than we were able to get it. So we actually did the training, and in a moment I'm going to kick off the training again for you so you can see what it looks like. But for right now, let's get to the performance. 17, you only had 17, so not too bad. In actuality, grad students, we had 8. And 6 of the 8 were identified as grad students. All right? Professors, we had 9, and 7 out of the 9 were predicted to be professors. Now, this is the holdout set, so this is actually generalizing. So not too bad. You might be caught watching Games of Thrones, but you know, it's better than even odds. Now, let's go ahead and go to the prediction and actuality, and let's see how well you can do on these. So we only had 4 errors, right? And if you know who this is, you don't get to vote. Graduate student, professor. Keep it in mind. Graduate student, professor. Okay. Graduate student, professor. Okay. Graduate student, professor. All right, here's the answer. Yes, professor. Graduate student, professor. But beyond that, the model actually did pretty well. And started to get really pretty good confidence. I was kind of surprised by that, but it started to get pretty good and have good confidence in the predictions that it was making. All right. Yes? So there's another type of problem that's called multi-labeling. And this is actually one. And this actually came up a couple of different times. It's kind of like, and you notice I was asking things like, are you in industry, are you postdoc, are you undergrad? There wasn't enough data to do that, but it's also another interesting problem because what you want the model to do is to put high confidence or high probability on both, you know, graduate student and, so which two are you? Undergraduate and professor? No. Are you PhD student? Right, who's also, yes, exactly. And then we had some people who wanted to be very, very precise. And it was like, I am faculty, I have my appointment, but I'm not there yet, and I'm still need to deposit. And I'm like, the network is not going to be able to determine that. You know, stress lines, or maybe, I don't know. But beyond that, just give me one, and we'll go with it. All right. So, some take-homes. First of all, frameworks such as Fast.ai have made deep learning accessible. Pre-training networks allows you to make powerful, useful models with far less data than needed previously. And now there are pre-trained models which do specific types of tasks. So I would suggest you visit Model Zoo, for example. These are pre-trained networks that do specific types of tasks in a pre-trained manner. One of my favorite is an animal pose detector. So if you have research where you have animals solving problems, for example, it actually can track, based just on the vision, where the digits are and what's happening, And it's a pre-trained network, and all you have to do is the same thing that we were just doing here. Give it some additional, label a little bit more data, but now you're talking about maybe a couple of dozen, maybe 50 before you're just up and running. And it has, gait detection, expression, all these pre-trained networks that are ready to go in some very esoteric areas. So, the other take-home message is that really none of this absolves us from thinking really carefully about the training data, both for the purpose because that's where everything is happening, and also because when we make mistakes or when we introduce bias, again, that is injected into the model in a way that's not easily found or uncovered. So thank you. Thank you for being kind. Thank you for being with us on the journey as we collected the data. Thank you for contributing your data and as we actually pulled it together and presented it to you. I'd like to invite you to visit us at the Data Science Institute, visit our website, follow us on Twitter. If you're an graduate student, you can stop by office hours Tuesdays, although not next week. And I'd also like to make an offer. If you're interested in a Fast.ai brief workshop, followed by a cohort they have for online courses, drop me an email. We'll be spinning this up. We'll be doing a sort of a test course over the summer, but in the fall, if there's interest, we'll actually spin this up into one of our workshop hands-on offerings. All right. Thank you very much. And do we want to take questions? We're over time, but no questions? Okay.
Okay, so I have a somewhat related problem that I'm interested in if this approach would be applicable to, which is it's not classification, but it's basically analyzing images and extracting features out of them.
Yes.
And we have a small data set, but we have the potential to pre-train something on a large analogous data set.
Yep.
So basically it's maps, and we're trying to pull features, identify features in the maps.
Yep.
And so would something like this
Yep.
work for that, or is this
Yep.
purely a classification thing?
No, it's a great question. There are pre-trained models for many different purposes, segmentation certainly being one of them. And sometimes, the pre-trained models have been pre-trained in areas that you wouldn't expect. Just had a meeting. Steve Wernke, is anybody from Steve's lab here? Yeah. Okay. Oh, yeah. There we go. Okay. Great. And we had a discussion before about possibly, using a pre-trained network. And one of the ones that I suggest that we looked at was from UNet, which was used for cells. But applying it to the problem of finding archaeological sites. So sometimes you can find really sort of left turn kind of solutions, but absolutely, it's not just classification. Also deep learning for natural language processing that changed the world just about 18 months ago with ULM-FIT. Very different way of doing natural language processing, image segmentation, all sorts of different types of problems with these types of pre-trained models. Other questions?
Yes.
Yes.
So speaking of retraining the model, do you think if you retrain the pre-trained data set on your local data, will that introduce bias? Will that reduce the bias in your training? How do you think using that, especially when you try to use those NLP data sets outside and try to reapply that in the clinical domain as well?
Right. And that's a great question. I ran into a similar problem when I was looking at EHR data a little while back before I started here. And my first thought is first go with the existing pre-trained models and see how well they do. Because if you think about it, much like V1, the lowest level features are going to be the ones that are least like what it was trained on in the first place. There exists a line, there exists an orientation, there exists a closed area. So similarly with natural language processing models, if you go low enough, then maybe you can still get the advantage of that pre-trained model. And so you start with, okay, let's just train the last few layers and see if I can still solve the problem. But if not, then start unfreezing further and further back. And if it just never works, then that means the data set is so different that yes, then you need to actually do some pre-training on your own data, and then you can tackle the problem as, do I have enough? Yeah. But one trick is to train it in a totally different kind of a task, and then you apply it to a new task. And that way you're not biasing it, at least for the outcome. Yeah. Other questions? Yes?
Yeah, my question has to do with cross-application. So you have this algorithm that it's used to seeing image kind of data,
yeah.
right? Or you talked about NLP. But what about something completely different, like something you would use a hierarchical linear regression, right? Something very different, but you're using this algorithm just applied differently to that kind of data.
So it really depends what question you're asking and what kind of answer you want to get out. So you notice in none of this was it was all qualitative. And the question may be, how good would it be? How much better than a human would it be? Andreas had actually asked me before, so come on, can you give me a metric? I want a metric of how well it's performing. And with small data sets, it gets pretty tough, but that's exactly why I was asking you all to make the judgments so you could compare yourself to the performance of the model. So inference, that gets more difficult. If you want to do inference or confidence interval type things with these types of approaches, then you're looking more along the lines of bootstrapping and trying to get answers that way, because they're not built necessarily for inference. Yeah. Other questions?
So I was just wondering if you could talk a little bit more on how you chose the architecture. I know
Sure.
it was pre-trained, and if you didn't use this architecture, what else might you use?
Yeah. So I used ResNet 34. 34 refers to the depth, and this is pre-trained on ImageNet, which is about 1 million images from Google. And the images are not graduate students and professors. So they're things like cars and peoples and cats and houses and all sorts of different things. But the value in that is that, especially that you gain from the lower levels, is it's your early visual cortex is essentially what you're getting early on. ResNet itself has been around for a while. And 2015, I think, was when the first paper came out. There are other more later architectures, but frankly, you kind of go with what works. So how many of you saw the autonomous driving day demonstration from Tesla? It was on Tuesday, I think. Really cool stuff. But do you realize, that's a lot of the network is VGG, is like old networks that underpin self-driving cars. So it's not necessarily the latest and greatest. You actually look to see what works for your particular problem. In this case, ResNet kind of works just because it solves some of the problems. With that disappearing gradient, it handles that really well. It's fast. You'll notice I did 34 rather than 50, which, they tend to get better and better. 34 worked well enough. But as I mentioned, I was not able to retrain any of the lower levels because I didn't have enough data. You go with what works. A lot of the field is like that. So the tweaks that I've talked about of changing the different learning rates, and there's one approach which is like sawtooth learning rates. So you have low and then you go fast and then you drop it down again. These are not theoretically motivated changes. So this is not the math and the theory driving what's happening. This is purely exploration and seeing what happens. It's a very different kind of a field, and you're going with what works, which is why they've not gotten into the area of, why you don't depend on this stuff to answer those types of questions. If you have a hierarchical linear model question, you better use a hierarchical linear model. Yes?
Did you tweak any of the parameters?
We did, actually. So, and that was what Richard and I were actually doing quite a bit of. And that was a fun thing. And just to give you an idea of just how quick this can be, so let's go ahead and we're going to just retrain this network right now. So, because it does change every time that you do it just a little bit. And here we go, and I'll answer the next question as it is retraining. This is running on a remote machine. This is on a Quadro P5000 network card or GPU card. Other questions, and or you may be just mesmerized by. It is done. So let's go ahead and see how well it did. I didn't look at the numbers. Yeah. Let's see how it goes. And I might just go ahead and do 4 epochs. Sort of avoid that overtraining, overfitting. Oh, that's right. Thank you. Yeah, that's right. Because otherwise it just. Oh, and actually that's what happened before. Because I didn't do that. I didn't execute that before, did I? So when you retrain, if you don't reinitialize, then you're adding epochs, and then it will eventually overtrain. Probably could do with just a few more. And this is actually what we're doing. We're trying different transforms on the data beforehand, trying different levels of this. I tried a ResNet 50 until you can look to see how well it can work. And we'll just look and we'll see what the interpretation of this is right now. Not good. Not good. Probably, if we did it a few more times, it would probably improve, yes. Other questions? Yes?
So again, like when you retrain data, do you think sometimes people just start torturing the data until they get the answers that they need? Like right now, once you started overtraining the model,
That's right. Mm-hmm.
I'm going to do this until they satisfy, oh, I got my results.
Mm-hmm. So the question is, can you? So the question is, if you sort of allow yourself to retrain and retrain, then could you be torturing the data until you get what you want? Absolutely. So that's why you do want to rerun. And so this one we didn't do it how we did it before, but you do rerun to make sure that you didn't just happen to guess. That's especially if you have a whole lot of 17 images. That's really not enough. If you have a large enough set. Then you can trust your validation set more, and then what you do is you have a true holdout set. Your true holdout set that you do not use until you are done. And then when you do that, and if it holds for that, then you can have confidence in. But that's the trick.
Having a pre-trained data set will not help with solving the overfitting.
Keep in mind that these pre-trained models are trained on totally different types of data. So the problem is that you can absolutely overfit, and you can see it some. You saw it happening right there. So you need these really designed for when I say smaller sets of data, I mean like 100 of each. For this particular type of model, I would have been comfortable with. Like 59 and 46, we're skating on the edge. Yes. Right. So the question was, how do you curate the data, and so you're not just picking up on things, because obviously the original model that we were looking at was not really going on the look of the person, it was going on what was happening around the person and detecting the environment that they were in. And if you wanted to be really careful and only get the person, then yes, and you need to do some work on your images. That points to the need of having an audit trail for all the work that you do on your images, and for you to actually version where you are with your data. Because your version, 0.2 of your model is not going to be reflected in your code at all. 0.2 of the model is going to be what data you use to train it, and you need to have an audit trail on all the things that you did to the data to get it to that particular point. And that's something which is challenging. We've gotten really good at versioning our code. We use Git, we use GitHub, but what we need is a Git for code, for data and for images, depending whatever your data is. We also need to carefully do our data manipulation in code. So you need to be doing it in notebooks, and you need to be versioning all of that work.
Let's thank Jesse again. Thank you for agreeing to do this.
And I'm never doing this again.
Oh, yes, you are. This is great. Thank you so much for coming to the symposium.